Lab 1, Constant Velocity by Shervin Praveen. The purpose of this lab is to measure an object's position in respect to time with no outside forces. From time 0 till the end, the ball was rolling at a constant speed with no change in direction. I modeled the video plotting the position in respect to time on Tracker and then created a visual using GlowScript. Finally, I compared the modeled graph and the actual graph to check for accuracy. After tracking the motion, we learned that there is a strong correlation between what was expected and what happened. Unfortunately, as time went on, we see our expectation did not match what happens. We will see this later. The main physics ideas and principles. Newton's second law. No acceleration means that there is no force. The position update formula. With constant velocity, we can predict the final position. And velocity update formula. Since there is no force or acceleration, initial velocity is the same as final velocity. This is visualized the Newton's second law and the position and velocity updates. The second law is to prove that there is no force since there is no acceleration. The velocity update is to show why final velocity is the same as initial velocity. The position update is used to predict the final position. We use Tracker to find the actual final position, and we use WebPython to model our video using code. This gives us a perfect world scenario. These are the reasons for our principles. The initial conditions for both the video and the model started on the origin and the ball having 0 force, velocity initial, and position 0. The system is a lacrosse ball and the surroundings are all other objects like the meter stick, whiteboard, and air. I started with Tracker. I set the starting point as the origin and set the scale. I plotted the position during 3.5 seconds. I created a model with GlowScript. I set force equal to 0 and found velocity by choosing 2 points and inputting this formula. Then we plugged in the update formula shown below. Finally, we compared the graphs in real life versus the model we created. From the starter code, we inputted the velocity we found from the previous slide. I set the time to run until 3.5 seconds and delta t to be 0.033 seconds. I set the force equal to 0 and inputted the update formulas mentioned earlier. There were similarities and differences between the data and model predictions. In the first second, the graphs were perfectly similar. This shows that creating a model can be an accurate prediction in terms of short times, but there was a big divergence after the 1 second mark. This shows that for large time increments, our computational model is not accurate. The sources of these errors. The error is caused by drag and friction. We know there is drag because the ball has area facing forward. We know there is friction because our ball is rolling instead of sliding, and these cause deceleration. If the axis was flipped, how would this change things? Flipping the axis would mean the ball is traveling in negative meters, since to the left would be positive and to the right would be negative. And negative meters is conventionally to the left side, but we can see that the ball is traveling to the right, so that wouldn't make any sense. And is it possible for you to say how many forces are being added together? In the perfect world, there's only gravity and normal force, since we're talking about net force being 0. But in the real world, we cannot know all the forces, since even a draft in the room can be a decelerative force. In conclusion, the results showed computational models can be very accurate for short times. It showed that real-world factors cannot be ignored, since we saw real-world deceleration, and highlights the importance of improving our models to match the real world.